Want to know where a function goes up or down without graphing? The derivative tells you instantly. Master the first derivative test to analyze function behavior with confidence and precision. Here's a step-by-step guide for the first derivative test. First, you'll need to find the first derivative. The derivative function reveals the rate of change at every point. Then you'll need to find critical points. So you'll solve f prime of x equals 0 or find where f prime of x is undefined. These critical points split the number line into distinct intervals for testing. Then you'll test each interval. You'll pick a test value in each interval and evaluate f prime of x. So what will that tell you? This is a visual guide to help you interpret derivative values quickly and accurately. When testing on the interval, if the derivative is greater than 0, that means that the function is increasing on that interval. The slope is positive and the function rises as x increases. If the derivative at the point that you test is negative, that means that the function is decreasing. Therefore, the slope is negative and the function falls as x increases. And if the derivative at that particular point is 0, that is a stationary point. The slope is 0, indicating a potential maximum, minimum, or inflection point. Let's look at our first example. Given the function f of x equals x squared minus 4x, we want to find the intervals on which the function is increasing or decreasing. So step number 1, we'll need to find the derivative. Using the power rule, f prime of x will be equal to 2x, that is the derivative of x squared, minus 4, that is the derivative of 4x with respect to x. Then we'll need to find the critical point. So we'll let our derivative f prime of x equals 2x minus 4 be equal to 0 and solve for x. If we add 4 on both sides and divide by 2, x is equal to 2. In step number 3, we'll need to test the intervals. So our critical point is x equals 2, meaning our first interval is from negative infinity to 2, and our second interval is from 2 to infinity. So you can pick any point on this interval in order to test. So let's say we pick x equals 0, because that is on the interval from negative infinity to 2. When x equals 0, f prime of 0, that means you substitute x equals 0 into your derivative. 2 times 0 is 0, minus 4 is negative 4. So since the derivative is negative, that means that the function is decreasing on that interval. Then we'll do the same thing for a second interval from 2 to infinity. Let's say that we pick x equals 3, but once again you can pick any point on the interval from 2 to infinity. When x equals 3, the derivative f prime of x, if we substitute x for 3, 2 times 3 is 6, 6 minus 4 is 2. 2 is positive, therefore the function is increasing on that interval. So once again, for the function f of x equals x squared minus 4x, it's decreasing on the interval from negative infinity to 2 and increasing on the interval from 2 to infinity. If we look at the graph, this is the graph of a parabola, and you can see that the function is decreasing up until 2, and then it's increasing from 2 to infinity. In this next example, given the function f of x equals x cubed minus 3x squared, we want to find the intervals on which the function is increasing and decreasing. So step number 1, we need to find the derivative. So the derivative of f of x equals x cubed minus 3x squared is 3x squared minus 2 times 3 is 6, and then x. So that's 3x squared minus 6x. You can factor out a 3x if you want to. That is the same as 3x times x minus 2. So in order to find the critical point, we let f prime of x, that is 3x times x minus 2, equals 0. So since we have a product here, if the first term or the second term is equal 0, we know that the product will be equal to 0. So letting 3x be equal to 0, x equals 0. And if we let x minus 2 be equal to 0, x has to be equal to 2. So our two critical points here are x equals 0 and x equals 2. Therefore, we have three intervals. We have the interval from negative infinity to 0, the interval from 0 to 2, and another interval from 2 to infinity. For our first interval, from negative infinity to 0, we can pick x equals negative 1 and evaluate our derivative at x equals negative 1. So if you substitute negative 1 into your derivative, you'll find that the derivative is 9, which is positive, meaning the function is increasing on that interval. Doing the same for a second interval, from 0 to 2, we could pick the point x equals 1, and substituting x equals 1 into our derivative, 3 times 1 is 3, minus 6 times 1, which is 6. 3 minus 6 is negative 3. Since our derivative is negative, the function is decreasing on that interval. And finally, for our interval from 2 to infinity, we could pick any point. If we pick x equals 3, substituting x equals 3 into our derivative, f prime of 3 is equal to 9. And therefore, since it's positive, the function is increasing on that interval. So if we look at the graph, you can see that the function is increasing from negative infinity to 0, decreasing from 0 to 2, and increasing again from 2 to infinity. In this next example, given the function f of x equals 1 over x, we'll need to find the intervals on which the function is increasing or decreasing. So first step, find the derivative. In order to use the power rule, you'll need to rewrite f of x equals 1 over x as x to the power negative 1. So the derivative f prime of x will be equal to negative 1 over x squared. Now we know that the function will be undefined when x equals 0 since x is in the denominator. So our two intervals will therefore be from negative infinity to 0 and from 0 to infinity. On the first interval, we can pick x equals negative 1 as our test value. And if we substitute negative 1 into our derivative, f prime of negative 1 is negative 1. Therefore, the function is decreasing on that interval. If we do the same for a second interval, from 0 to infinity, if we pick x equals 1 as our test value, substituting x equals 1 into our derivative function, that will be negative 1 over 1 squared, which is negative 1. So the function is decreasing as well on that second interval since the derivative is negative. So when working with rational function, the derivative may be undefined at certain points, but these points create natural boundaries between intervals that must be tested separately. In this case, we saw that the function is decreasing on both intervals, but is separated by a vertical asymptote at x equals 0. And if you need any help on how to find vertical asymptotes, you can check my lesson on asymptotes. So here's your challenge for today. Apply the first derivative test to analyze this function. We want to find where the function f of x equals x squared plus 2x is increasing and decreasing. So remember the steps. You'll need to find the derivative, f prime of x. Then find the critical points. Set the derivative equal to 0 and solve for x. And finally, choose the test values in each interval and evaluate the sign of f prime of x. You now have the tools to analyze any function's behavior using derivatives. The first derivative test reveals where functions increase, decrease, and change direction, all without graphing. Practice these techniques regularly to build confidence and speed. And if derivatives feel overwhelming, I created a free fast-track derivatives cheat sheet that walks you through every rule step by step. You can download it using the link below. Thanks for watching. Please like and subscribe for clear, fast-paced math lessons that make math concepts click. And remember, math success starts when you stay on the fast track.